Hello, Betsa. Thanks for joining.
Welcome. Do you want me to monitor the YouTube?
Yes, please.
Okay, sure.
Okay. Betsa, are we live? Yeah, I think we are. Okay, good.
Yes, we are.
Okay, hello everyone. Thank you for joining, and sorry again for this little delay that we usually have when we start the live stream. Today we are going to continue with our lectures on heterogeneous systems, and what we are going to cover are the basics of the very basics of GPU programming. Let's say that the very first thing that we need to learn when we start writing a program for a GPU. This is what we call the GPU software hierarchy, which you will see it's organized into grids of blocks of threads. Please don't hesitate to ask any questions. Don't hesitate to interrupt me or write the question in the chat. I will try to pay attention to it. So very briefly, let's recap on what we learned in our previous lecture. GPUs are SIMD engines underneath, as you may remember. Recall also this plot here, this graph here, where we can see the amazing evolution that GPU hardware had in the last 12 or 13 years. And from this GTX 2085, there was actually one generation of even older GPUs that had the same architecture as this one, but they were slightly smaller, wimpier, with less number of cores. And then last year in 2020, this A100 got released. So this is the A100 block diagram. As you can see, it contains the current products containing up to 108 cores, GPU cores, but if you count the total number that we have in this layout, you will count up to 128. And each of these different cores contains like multiple SIMD functional units that are used to execute different types of operations for different data types, like integer 32 bits, floating point 32 bits, floating point 64 bits. And then we also find here load and store units to access the memory. And we have these special function units as well. And in the last three generations of the architecture, we also see these tensor cores, which are kind of specialized SIMD units for machine learning. They essentially implement very fast or execute very fast dot product operations, as you may remember from the previous lecture. Recall also, this is something important to keep into account also from the perspective of the software of programming. So that's why we have this slide here to recap on the fine-grained multi-threading paradigm that GPUs also employ. The idea of fine-grained multi-threading is that we have multiple threads that are scheduled in different cycles, and there is some thread scheduler that fetches one instruction from a different thread in different cycles and issues this instruction onto the pipeline. In the case of GPUs, fine-grained multithreading is fine-grained multithreading of warps. This is why here in this figure you see the thread warp 3, thread warp 8, and so on. In the end, each of these warps works as a thread in a, let's say, traditional fine-grained multi-threaded architecture. And the good thing is that after starting the execution on the SIMD pipeline, and here you can identify the different stages of the pipeline, there might be some operations that take longer. For example, memory accesses in case that we have a miss in the cache hierarchy. And in that case, the warp needs to go to memory and bring data, bring one cache line or multiple cache lines maybe from memory. And this is a long latency operation that might take hundreds of cycles. And this is why it's good to have other threads and other warps ready for execution, such that we can hide the latency of the long latency operations. That's the key idea behind the fine-grained multi-threading technique. And also recall, depending on what's the number of processing elements that we have, the way that the execution for the different threads happens might depend, right? So if we only have a single functional unit, as in this case, all the threads of the warp are going to be pipelines, so they are kind of parallelized in time. If we have more than one of these functional units, we can parallelize in time and in space. And remember as well that each of the SIMD lanes has access to a certain number of registers. We have a whole register file that is partitioned across the different threads that take part of the execution in one warp. So this is what we call a lane. And yeah, we will keep talking about SIMD lanes and registers in this lecture and in future lectures as well. And also, yeah, related to the execution on these functional units, as we have seen in the two previous slides, the way that instructions are scheduled on the different units, it's very similar to the way that in the GPU for the warps is very similar to the way that instructions are executed and are issued on a SIMD engine or on a traditional SIMD processor. So yeah, in this case, we, instead of issuing vector instructions, we issue instructions for different warps onto the different units that take part of the GPU core. And now let's start with our first GPU programming concepts. Why it's important to learn GPU programming? Because it's pretty useful. It's not only useful because you can exploit the huge amount of hardware parallelism that GPUs have, but also because it's kind of a good way of learning parallel programming as well. It's we are going to, in this course, we are going to study, or we are already studying, the CUDA programming language. We will also talk about OpenCL programming language, which is very, very similar. We will mention OpenCL from time to time, but even though they are originally intended to for programming GPUs, they are both synchronous paradigms, both synchronous parallel programming paradigms, and they are useful for different other languages and parallel devices as well. So whatever learnings you get from this course about GPU programming, they will be for sure applicable to your knowledge on parallel programming in potentially other devices as well. And programming using these SPMD model, SPMD programming model, as we discussed in the previous lecture, makes programming GPUs much easier than it used to be to program SIMD engines or SIMD processors. So general purpose processing on GPU, easier programmer, as I was saying, easier programming of SIMD processors with SPMD, the single program multiple data programming model. GPUs were definitely a revolution more than 1 decade ago when they started to be used for general purpose computing in high performance computing applications, for example. A few years later, they started to be used for machine learning and artificial intelligence, and today they are definitely the most used accelerator. And the good thing of GPUs is that they provide a huge amount of parallelism and a huge amount of processing elements that can be used by many, many workloads, because there are many, many workloads that show or exhibit inherent data parallelism. Examples are linear algebra computations, where we use, for example, matrices, or image processing, because images, as you know, typically are composed by hundreds, thousands, or millions of threads, or more recently, deep neural network and other networks and other machine learning workloads. However, programming, learning how to use GPUs in a smart and optimized way is not for free, right? It's not only that we need to learn a new programming model, you need to learn CUDA or OpenCL, but also the fact that you need to rethink the algorithms and the way that these algorithms map onto the hardware, right? Because so in some sense you need to re-implement your applications because the architecture is different from the architecture of a CPU, and we need to tailor the algorithm, the implementation of the algorithm as much as possible to the specific characteristics of the GPU hardware. And even though GPUs are super powerful processors, there are still bottlenecks. We can talk for sure about the DRAM memory bandwidth, because even though we have GPUs with GDDR5 or GDDR6 memory, or even HBM2, which have greatly increased the amount of bandwidth that is available to the GPU cores keep being faster than the access to data. So we still have that point, that problem. Another additional bottleneck is the fact that the GPU is a discrete device, typically connected to the host CPU via the PCI Express bus, or in the case of NVIDIA GPUs with the NVLink bus. But still, even though the bandwidth of these buses increases over time, also the compute power of CPUs and GPUs increases over time, and even faster, right? So that's why these CPU, GPU, and GPU, CPU data transfers are still a bottleneck, even though from the programmability perspective, there have been many advances in recent years. And we will talk about that in later lectures, but let's start easy. Let's start simple. Recommended readings for sure for the whole course. I would recommend you this book, Programming Massively Parallel Processors, from Professor Wenmei Hu and David Kirk. The current edition that you can already now find in the library or Elsevier webpage is the third edition. As far as I know, they will release very soon the fourth edition. And also the second most important, if not the most important reference, is the CUDA programming guide. It's a very comprehensive guide that covers many different, all aspects of programming the GPUs using CUDA, from the simplest concepts similar to the ones that we are going to cover today to the most advanced features. And NVIDIA folks review this documentation very frequently and add many details about the hardware and the software over time as new features are included in the CUDA SDK or in the GPU hardware itself. Okay, you already know what's a GPU internally, but I always like to show this slide when I start talking about the GPU programming, because here we see, like in a very simple way, we see how different CPUs and GPUs are, because essentially the area, the die, is spent on different purposes. While in CPUs, we have only typically a few out of order cores, and then we have a few ALUs, and we have most of the area of the chip is spent on control hardware and cache. Usually the GPU is exactly the other way around. What they have is a lot of small compute units, all these SIMD engines and SIMD lanes that we have discussed in the previous slide. However, they are much simpler. These cores are usually in order cores, so they don't need so much control logic as if they were CPU or out of order CPU cores, and also caches are pretty small as well, as you will see. It's not the same for the register file. The register file in the GPU cores is pretty large, especially if we compare to the register file in CPUs. But yeah, as I said, we will keep talking about this in later lectures. So Let's start talking about how we organize computation when we are doing GPU computing. First thing is that the computation is offloaded to the GPU. We are executing something on the CPU, and at some point we find some region of code that is massively parallel, and it can take advantage of the execution on the GPU. So that's what we do. We transfer the control to the GPU. We offload the computation onto the GPU. And typically we have 3 steps in this operation. We actually have 5 steps, but let's first talk about these 3 steps. In the first one, we have to transfer data from the CPU memory to the GPU memory. For example, this matrix here, we are going to operate on this matrix here. Recall that CPU memory and GPU memory are connected via some bus like PCI Express, and that's the first step. We have to copy data from the CPU memory to the GPU memory, input data. And then we start what we call the kernel execution, which is the execution of a program or of a function that is called kernel on the GPU cores. It will take longer or shorter, and at some point, GPU cores, all threads running on the GPU cores will finish the execution, and at that point, the control is returned to the CPU. And then it's time to retrieve the results that have been generated on the GPU memory. And to do so, we launch a data transfer from the GPU memory to the CPU memory. Okay, then the other 2 steps that I mentioned in the beginning of this slide are memory allocation and memory deallocation, right? Observe that we have 2 memory spaces: the CPU memory, that is a host memory, we typically call it main memory, and then we have the GPU memory, we normally call it global memory. So there is some data movement between main memory and the global memory of the GPU. But before doing this data movement, we have to allocate data in both the CPU memory and the GPU memory. So observe that when we are using GPUs in our heterogeneous systems, we normally, or in principle, we have to do double allocation of every single array that we are going to use on the GPU memory. We have to allocate in CPU memory, we have to allocate in GPU memory, then we copy from one to the other one. And at the end of the program, we will deallocate memory. We will free the memory space in both memories. Okay, let's continue with the traditional program structure. So we normally execute threads, let's say coarse grain threads on the CPU cores, and we execute kind of fine grained threads that compose and execute the GPU kernel that runs on the GPU. So because we have 2 different devices on the system, one of them is optimized for latency. The CPU is like that. It has a single thread or a single core or a low number of cores, and these devices are optimized for fast execution of a single thread. And we also have another device, which is the GPU, which is designed for massively parallel execution. That's what we are going to do, right? We will make use of the CPU in those parts of the code that are more serial or sequential, or maybe modestly parallel, and we will use the GPU when we have a massively parallel section to execute. And at some point, this massively parallel section will finish as well, and we will return the control to the CPU that will continue with some execution of serial code, and then again, we may launch a new, maybe the same kernel or maybe a new kernel onto the GPU device. And here you can already see what's the syntax for these calls to these kernel function, GPU kernels or GPU functions that are executed by the GPU threads. Recall as well the SPMD programming model. It's a programming model, it's not a computer organization. And it allows us to have each processing element executing the same procedure, except on different data. Right? That's what each of the individual threads that run on the GPU are going to do. As we mentioned in the previous lecture, and we will see probably in the next lecture, these different procedures, these different threads can synchronize at certain points in the program. Those are what we call barriers. But as I said, we will talk about them in our next lecture. And essentially what we have is multiple instruction streams executing the same program. But each of these programs or each of these threads work on different data and can execute different control flow paths. As we saw in the previous lecture, divergence was possible thanks to the use of predication and masks that allow these different control flow paths. Okay, let's continue with the CUDA and OpenCL programming model, with the SPMD programming model. As I mentioned as well in the beginning, this is bulk synchronous programming. And this essentially means that we launch hundreds or thousands of threads to compute on many different input data. And at some point, these threads have to synchronize. The way that they do is synchronizing in a coarse-grained manner. That's why we talk about bulk synchronous programming. So recall that we execute kernels on the GPUs. At some point, one kernel terminates, and that's the point where all the threads that executed the kernel synchronize. So this is a global barrier or a coarse-grained barrier that synchronizes all threads. And after that point, we can launch a new kernel, and then new threads start with the execution. So the host, typically the CPU, allocates memory, copies data, and launches kernels. So we still have a main CPU thread that controls everything and decides when to offload the computation to the GPU memory. And then we have the device, typically a GPU, that executes kernels. One thing to clarify here, why do we say typically CPU or typically GPU? In case of CUDA, I think there is no difference. I mean, we always have a host, which is a CPU, and a device, which is an NVIDIA GPU. In the case of OpenCL, OpenCL, even though it's very, very similar, even in the syntax, very similar to CUDA, and this software hierarchy, it's different in the sense that it is cross-platform. And what this means is that there are OpenCL distributions for different devices, not only GPUs. We also find FPGAs that can be programmed using OpenCL. We have other devices like DSPs. We have GPUs from different vendors for sure. Some time ago, we even had Intel Phi many core processors that were also programmable using OpenCL. And even the CPU, you can program it using OpenCL. So in an OpenCL program, you can have the host being a CPU and the device being the same CPU as well, for just to give you an example. And how is the computation organized? This is what we are going to talk about today. But as I said in the very beginning, in the first slide, we are going to talk about grids, blocks, and threads in CUDA. The name that these receive in OpenCL is ND range, work group, and work item respectively. But yeah, don't worry about these terms for now, because we are going to continue talking about them. We continue with the traditional program structure in CUDA. Function prototypes. This is for you to see what's the difference between a CPU function like this serial function that will run on the CPU, maybe using one CPU thread or more. And then this is the prototype of the function that runs on the GPU, the kernel. Notice that we use this qualifier global to identify this function as a kernel for the GPU. And then in our main function of that runs on the host code is where we are going to carry out with different steps. First of all, allocate memory space on the device. Recall that we also need to allocate on the host, and we allocate on the device. We do so by using this CUDA malloc API, where we use a pointer, which is a pointer that points to the memory space that we are reserving, and we are reserving a certain number of bytes. And then we transfer data from the host to the device using this CUDA main copy. We are going to see more details about this API in the next slide. And then we define what's the execution configuration. I'm going to talk about the execution configuration soon, but as you can already see, this what we call the execution configuration is the number of blocks and threads that we are going to use in our program. And then we launch the kernel. We have to pass to the kernel the execution configuration and then some arguments, some input arguments or parameters. And after determination of the kernel, we transfer results from the device to host using, again, CUDA main copy, as you can see. And this process might be repeated multiple times, maybe because this is an iterative algorithm and we launch this kernel multiple times, or maybe because the program is composed by multiple serial code parts or serial code sections and parallel code sections that run on the GPU. And then we will go step by step, going onto the details of the GPU kernel and how to program it. But yeah, there are a few things that I can already tell you. In the end, you will see your first kernel very soon. We are essentially writing C code, and there we can use automatic variables. These automatic variables normally are assigned to the registers, but also inside the kernel, we can use an on-chip memory space that is called the shared memory. We will see how to use it. We will start seeing how to use it in the next lecture. And also the threads that run on the same core can also synchronize using this specific API that you can see here. And these are the barriers that I mentioned a couple of slides ago. But as I said, we will go into the details on these details that I just mentioned in later lectures. So yeah, more details about the APIs that I mentioned in the previous slide. CUDA, in CUDA programming language, this is the syntax for the memory allocation, CUDA malloc. This is the pointer to the memory space that we allocate, and this is the total number of bytes. So as you can see, the syntax is very similar to a normal C malloc. Then we have memory copy. This is the destination. This is the source pointer. This is the number of bytes, and this defines the direction of the copy. It's a CUDA main copy from the host to the device. This is why this D-in is the destination, and this H-in is the source. Notice that we have marked these two arrays, one in the CPU memory, the other one in the GPU memory, with a single letter just to distinguish what's allocated in the host and what's allocated in the device and what's allocated in the host. And as you can imagine, when the data transfer happens from the GPU memory to the CPU memory, instead of writing here host to device, we will write here device to host. Okay, so then next thing that we also saw in the previous slide is the kernel launch. This kernel is the name of the kernel, and this is the execution configuration. You can see already here the number of locks, the number of threads that we are going to use, and the arguments, and finally the memory deallocation, CUDA free. Instead of using free as we do in C, we use CUDA free. And yeah, and finally we will talk about this also in a later lecture. But we sometimes will use this explicit synchronization that is used. It's an API that we use in the host code when we want to get notified about the termination of a kernel on the GPU side. But as I said, we will have time to talk about this in later lectures as well. And this is the first code example that we are going to see. This is code for a simple operation, which is vector addition. We are going to talk about vector addition in the next slide, but for now, you just need to know what you already know for sure. What's a vector addition? You have two input arrays or two input vectors A and B, and you have one output vector C, and we perform the element-wise addition of these vectors. But when we write code for a GPU, we will have some host code and we have some GPU code. In the host code, what we need to do, as we discussed in previous slides, is first allocate memory. We assume here that the memory on the CPU has already been allocated, and also the data, let's say these float A and float B initialized already. And then we call this function, which is a C CPU function, and then inside it, we first allocate GPU memory. This is for A, B, and C in the 3 cases, because it is a vector addition, they have the same size, and then we copy data from the host memory to the global memory or to the device memory using our CUDA and copy host to device. Then we launch the computation on the GPU. This is some code that for now we are missing here. When the kernel terminates the execution on the GPU, we can copy back the results from the GPU memory to the CPU memory, which in this case is the array CD in GPU memory. C is the destination in the host memory, and now observe that the copy is device to host. After the all computation needed for these arrays A, B, and C, we will deallocate using CUDA free. But let's talk about the kernel itself, which is the thing that we really want to learn how to program in this course. And this is our first GPU programming example. As you know, in vector addition, what we do is the element-wise addition of 2 vectors. Very straightforward assignment of this computation to the GPU threads is assigning 1 GPU thread to each element-wise addition. So each of these green lines that I draw here represent the GPU threads. So the first, this GPU thread 0 or thread first thread is going to execute this addition here, A0 plus B0. And this is the computation assigned to the next thread, which is thread 1, let's say, and this is the computation assigned to the rest of the threads. And here we may have, how many do we have? We have n threads, right? This n might be huge. This n might be millions. So this whole amount of, or this whole set of threads is what we call a grid of threads. But recall, this n might be very, very large. We might be talking about millions of threads, right? And of course, these millions of threads are not going to run all on the same GPU core. We have to find a way of partitioning this grid with 1 million threads and assign them to the GPU cores. You already know that we have a certain number of cores on the GPU hardware, 128 in its maximum in the A100 architecture, right? So in order to do so, what we do is grouping threads into what we call blocks, thread blocks, or simply blocks. And these are called work groups in OpenCL. So the first 4 threads will create block 0, the next 4 threads, block 1, block 2, and block 3. And we assign some of the computation to each of the blocks. This is the part of the output array C that the block 0 is going to compute. This is block 1, block 2, and block 3. And then inside each of the blocks, we distribute the computation, in this case, these 4 elements among the available threads, in this case, 4 threads. And this idea of using thread blocks or blocks is good to map the program regardless of the characteristics of our GPU in an efficient manner. This is why we talk about transparent scalability. In our program, we define a grid, a kernel grid, or a grid of threads that are going to execute one kernel, and we group the threads in the grid into blocks. In this case, we have 8 blocks, right? So we will typically have many more blocks than that, but this is a toy example where we are using only 8 blocks. And then we write this program once, and we can schedule, we can schedule and we can launch this program on different types of GPUs. Some of them will be less powerful, others will be more powerful. In this device, this GPU, we only have 2 cores. In this one, we have 4 cores. We have a thread block scheduler in both devices, and depending on the number of cores, this thread block scheduler will assign assign thread blocks to the cores. So one possible way of doing the assignment in this device with 2 GPU cores is block 0, block 1, block 2, block 3, block 4, block 5, and so on. And in this case, we can terminate earlier because we have 4 GPU cores, and we can schedule more thread blocks at once. So yeah, and actually, by the way, here you see that we have assigned 1 block per GPU core. Normally, it will be more than that. So normally, GPU cores can hold up to, I think it's, I don't remember exactly, but it might be 16 to 32 blocks, if not more, in current GPU generation, something like that. But this is like a simplified example, as you can see. So each block can execute in any order relative to other blocks. This is also one important consideration here. Even though you see that we have scheduled them in order in some way, we have no guarantee that block 0 is going to get executed before block 5. The GPU hardware doesn't guarantee that. We cannot make that assumption. And if we want to synchronize these blocks in some way at some point in our program, we will have to terminate the kernel. That's why we are using this bulk synchronous programming model. Okay, now let's launch a kernel. So we have threads in the same grid executing the same function, non-kernel, and a grid can be launched by calling a kernel and configuring it with the appropriate grid and block sizes. So this is our kernel call. In this case, the kernel is called back@ kernel. This is the execution configuration, and these are the arguments. And in the execution configuration, what we see is the number of blocks and the number of CPU and the number of threads per block. So as you can see as well, all blocks use the same number of threads per block. In this example, this number is 512. This might be a different number. Usually will be something between 32 and 1024. But yeah, we will talk about this later as well. And then for the total number of elements that we have in vectors A, B, and C, for example, we need a number of threads, and this number of threads are grouped in a number of blocks. So that's why the number of blocks is obtained as n divided by the number of threads per block. And now we can so recall this host code for the vector addition example. What we were missing here is the execution configuration, the number of threads per block, and the number of blocks, and the call to the kernel, to the GPU kernel. And now let's see how this GPU kernel looks inside. And actually, we have already seen it in the previous lecture. Remember this slide that we have this CPU code, which is just a loop with 100,000 iterations where we are adding elements with the same index. So it's a vector addition, right? The vector A, vector B, we are adding element by element and storing in vector C. The CUDA code is really very similar. As you can see, what we are doing here is reading one element of A, reading one element of B, adding them and storing them in the array C. The only difference is that we replaced this for loop here that was is executed on the CPU code using a single thread and repeating this operation many times. Instead of using this for loop, what we do is using a thread index. And we are going to talk today about how we calculate, how we obtain this thread index. The index in the end is the index that represents each of the individual threads that run on the GPU. Okay, this is already something that you know. The vector addition kernel, same as any other kernel, is preceded in the declaration by the keyword global. And then there are also other keywords, special keywords that we use inside the kernels. These are the block index. There are a few more, but these are the first ones that you are going to learn: the block index, the block size, and the thread index. And let's see how we use them. So recall that in a CPU, we execute these using a for loop, and we repeat many times the computation, each of the iterations, to go over the whole content of vectors A, B, and C. Here we replace the for loop with the calculation of this index, and this I is kind of a global index for all the threads that we are using. Inside each block, we have a number of threads per block, which is represented by this block team X inside the GPU kernel. This is what we had in the execution configuration the number of threads per block when we launched the kernel. So the number of threads per block multiplied by the block index plus the thread ID inside the block give us the the global index for this thread, and tell each thread what element of A, element of B, and element of C they have to read. There is one thing to consider here, one thing to take into account as well here is the boundary conditions, because recall, we are using a number of blocks, and the number of blocks, or the number of threads per block is fixed. In the example that we saw a couple of slides ago, it was 512. So what this means is that the size of the input should be a multiple of 512. Should it be a multiple of the number of threads per block? No, not really. But what should we do in the case that the size of the input is not a multiple of the number of threads per block? So in this case, what we do is launching more threads than what we need. We launch the ceiling of the number of threads that we really need. If we have n, we would like to launch n threads, but n is not a multiple of 512, it's not a multiple of the number of threads per block. So we have to launch the closest multiple of 512, the closest multiple to n. This is the ceiling. So, and this is how we calculate this ceiling, or you can also use the ceiling function that C libraries provide. And then the kernel code is slightly modified because we need to check the boundaries, right? So there will be a few threads at the very end of the whole grid that we don't really need. Imagine that this, imagine that this n is 1000, and we are going to launch 2 blocks of 512 threads, which means that we have in total 1024 threads. Because n is 1000, the last 24 threads are going to remain idle, and they will remain idle because when they reach this if condition, they won't go into the body of the if, and they will simply return, terminate the execution, and only 1000 threads will be executing these operations here. Okay, in terms of compilation, as you can see, as we have already discussed, we have C code and CUDA code in our programs. The CUDA SDK provides the NVIDIA CUDA compiler. This CUDA compiler can distinguish between C code and that is later compiled by a host C or C++ compiler and executed on the GPU. In the case of the GPU side, the MVCC compiler generates an intermediate representation that is called PTX. Is kind of a virtual ISA code that is common to all GPU architectures, NVIDIA GPU architectures, and then it uses a just-in-time compiler to generate this device assembly, which is the actual machine code that is going to execute on the GPU. It's going to run on the GPU, as you can see. Okay, yeah, let's continue. So we are going to kind of recap on what we have just seen by talking about another example. In this case, we are going to start talking about image processing. And recall that images are two-dimensional data structures, right? So they have 2 dimensions. It's not the same as the vector, where we have n elements. Here in a matrix, we have a number of columns and a number of rows of the image. So that's the dimensions, height times width. And this can be an image. In this case, this image is 8 by 8, and each of the individual elements of these, we can call them pixels. Each of these elements here is usually referenced by using an expression like this, where J represents the row where a pixel resides, for example, row 2, and I represents the column, for example, column 3. So this pixel here is image 2, 3, right? So the image is a 2-dimensional organization. This is another example, image 0, 1, or image 1, 2. But this is a 2-dimensional organization, but how is this stored in memory? And that's important to understand because that also determines how we are going to access the data in the memory of the GPU. And this is, it's simpler when we are using one-dimensional data structures. It's a little bit trickier when we are using two-dimensional or three-dimensional data structures. It's a little bit trickier, but it's not difficult, as you will see. And as you know, an image as a two-dimensional organization is stored in memory with a linear layout. In this case, we are using a row major layout. So every element, image ij, in reality resides in this position, right? So in the end, because memory is linear, each row of the image is stored after, so for example, after the previous row of the image. So for example, this is row 0. So row 0 in the linear memory is until here. And then this is row 1. Row 1 in the linear memory is here, and so on. So there is a, let's say, certain stride from the first element of one row to the first element of the next row, right? And for each individual element, each individual pixel of the image, we can obtain the actual address of the image in the linear memory by using this expression as we have seen above. So if this is element 0, 1, it resides in row 0. So row 0 times 8, which is the width of the image in this case, plus 1, which is the column where the pixel resides. And this is element 1, 2, and we do similar calculations for this element 1, 2. So now when it comes to distributing this input image across the whole grid of threads that we are going to use in our program, and notice that I'm not talking at all about any specific computation. I'm not talking about any algorithm. We will see later some example algorithms of image processing. But for now, we are just discussing how we assign threads to each of the elements of the image, each of the pixels of the image, and how these threads are going to access these pixels in memory. So let's assume for now that we are going to assign one GPU thread per pixel. We are going to use a grid of blocks of threads, but this is going to be a one-dimensional grid, which means that we only have threads in one direction, right? We have a number of thread blocks from 0 to m, and a number of threads per block from 0 to n, or from 0 to n minus 1. We use these keywords inside the GPU kernel, and you know already some of these, right? So this is the block dimension. It's the total number of threads per block. This is the block index that identifies each individual block of threads. This is the thread index that identifies each thread within a block. And finally, you also have this grid dimension that tells us what's the number of blocks in the whole grid of threads. So how do we distribute the two-dimensional image among these one-dimensional grid of blocks? Well, we are going to assign consecutive pieces of the image to consecutive blocks. This is for block 0, and this is for the rest of blocks, block 1, block 2, block 3, and so on. Now let's see how we assign the computation inside block 0. So inside block 0, we will use 4 different threads. We are assuming a toy number, a small number, 4 threads for now. So thread 0 will work on this pixel, thread 1 will work on this pixel, and so on. And when it comes to accessing each of the individual pixels, what we have to do is using the block index, the block dimension, and the thread index, as we did before in the vector addition example. So as you can see, there is no real difference between the between accessing the one-dimensional data, which is the vectors, or the two-dimensional data as the image, if we are using a grid with the same characteristics, a one-dimensional grid. In the end, this image is stored as a linear array in memory. So this is how we can have each thread, in this case, this thread in this block, or thread 1 in block 6, it's accessing this pixel here, which it's actually in the address 25 of the whole image. And we can reason in a very similar way about how to do when we are using two-dimensional grids. They are actually more suitable, let's say, for two-dimensional data structures, as you can imagine. And also, it's also possible to have three-dimensional grids. We don't need to go into that detail because in the end, if you understand well how one-dimensional grids are indexed and the memory access happens, you can also understand how it's for 2D and 3D grids. So in this case, we have blocks we have two-dimensional blocks, and we have blocks in both dimensions of the grid. So now we have a number of blocks in the X direction and a number of blocks in the Y direction. So this is represented by grid dim X and grid dim Y. So in total here we have 4 by 4 blocks, as you can see in this example. And then inside each of the blocks, we have a number of threads, in this case, a total number of 4 threads, but we also have 2 dimensions. So we have 2 by 2 threads inside each block. In particular, the block that is going to work on these pixels in particular is block with block index X2, block index Y1. And this is thread with thread index X1 and thread index Y0. And when it comes to fetching one element or grabbing from one element from the image for computation, what we do is something like this. We compute the row and the column where the particular pixel resides by using the block index Y block, the dimension of the block in the Y direction, the thread index Y, and same thing for the column, but in this case using the X dimension instead of the Y dimension. So you'll see this element, for example, is in row 3 and column 1. So the way that we calculate the row and the column is based on the thread index and the block index. Okay, we are almost done for today. You know already that when it comes to writing a GPU kernel, the code that is executed on the GPU hardware, we need to define a grid of threads. This grid of threads is divided into multiple blocks, and then these blocks are assigned to the GPU cores. And actually, you already saw this slide in the previous lecture. Recall as well, something that I mentioned is that after assigning the blocks to the GPU cores, they are divided into warps, and these warps are these SIMD units of 32 threads that are executed instruction after instruction on the available SIMD lanes, on the SIMD engine that each of the cores is. If you are interested in reading about the topics that we covered today, I would definitely recommend you Chapter 1 and Chapter 2 from the book Programming Massively Parallel Processors, and that's all for now. In our next lecture, we are going to talk about the memory hierarchy of the GPU from the hardware and from the software perspective as well, because it's really important to understand all the different, understand and learn how to use all the different memory spaces that the GPUs have in order to be efficient and write optimized code. That's all for today. Are there any questions, guys? Any questions in the chat, Behzat?
I don't see any question, Juan.
Okay. Thank you, Behzat. Yeah, I assume there are no questions from our